Welcome to Corrupted Files. Today, we're exploring the Programming Languages Iceberg. If you're new to Iceberg videos, here's how this works. We start at the surface with things everyone recognizes, then slowly descend into increasingly obscure, strange, and sometimes disturbing territory. At the top, everything feels normal. By the bottom, we'll be talking about languages that barely function, languages created as jokes, and languages that blur the line between programming and obsession. Research quality equals video quality, so this one goes deep. Let's start at the surface. These are the languages almost everyone has heard of. Even if you've never coded, you've probably seen these names before. Python. We'll start with Python, because at this point it's everywhere. Python was created in 1991, but its popularity didn't explode until much later. Today, it dominates fields like AI, machine learning, automation, cybersecurity, and data science. The reason Python is so popular is simple. It's readable. The syntax feels close to plain English, which lowers the barrier to entry without limiting what advanced users can do. Interesting fact: Python isn't named after the snake. It's named after Monty Python. The creator wanted programming to feel fun instead of intimidating. Python feels modern, but it's been quietly waiting in the background for decades. Next is JavaScript, the language that runs the modern internet. If a website is interactive in any way, JavaScript is involved. Buttons, animations, live updates, forms, all of it. JavaScript is popular because it's built directly into web browsers. Over time, it escaped the browser and now runs servers, desktop apps, and mobile apps. Here's the part people always bring up. JavaScript was created in 1995, and it was written in just 10 days. That rushed origin explains why JavaScript is powerful, flexible, and also confusing in ways that feel intentional. Despite the name, JavaScript has almost nothing to do with Java. That was a marketing decision, and developers are still dealing with the confusion decades later. Java is a completely different kind of popular. It was created in 1995, the same year as JavaScript, which is why people still mix them up. But Java lives in the enterprise world. Banks, governments, insurance companies, and Android apps rely heavily on Java. It runs quietly in places most people never see. Java became popular because of one promise: write once, run anywhere. The idea was that Java programs could run on different systems without modification, which made it perfect for large organizations that care about stability. Interesting fact: Java was originally designed for interactive televisions. That project failed, but the language survived and found a much bigger purpose. C++. C++ is where things start to feel more serious. It was created in 1985 as an extension of the C language. Originally, it was literally called C with classes. C++ is popular because it gives developers extreme control over hardware. It's used in game engines, operating systems, real-time simulations, and performance-critical software. The downside is that C++ doesn't protect you. A small mistake can crash an entire system or introduce bugs that are almost impossible to track down. It's powerful, dangerous, and respected, which is exactly why it's still here. C# came later, released in 2000, and is often described as Microsoft's answer to Java. It became popular because it integrates deeply with Windows and the net ecosystem. It's also massive in game development thanks to Unity, which introduced C# to millions of developers. Interesting fact: the name C is pronounced C#, like the musical note, implying it's an evolution of C. Over time, C# grew into a flexible language used for desktop apps, web backends, cloud services, and games. PHP. PHP is one of the most controversial languages on the surface level. It was created in 1995 and became popular because it made web development easy early on. You could upload PHP to a server and instantly create dynamic websites. Interesting fact: PHP originally stood for Personal Home Page. It started as a collection of personal scripts, not a serious programming language. Despite constant criticism and jokes, PHP still powers a massive portion of the internet, largely because of platforms like WordPress. PHP refuses to disappear. SQL. Finally, we have SQL. SQL is different from everything else here. It's not a general-purpose programming language. It's a query language designed specifically for databases. SQL is popular because it's incredibly efficient. One SQL query can replace hundreds of lines of regular code. SQL dates back to 1974, making it the oldest language on this tier. Long before modern apps, SQL was already organizing data. Also, no one agrees on how to pronounce it, and those arguments have definitely ended friendships. We're moving just below the surface now. These languages aren't obscure. Most developers have heard of them, many use them daily. But unlike the surface tier, these languages aren't universally agreed on. They come with opinions. They come with design philosophies. And there where programming starts to split into different worldviews. This is Tier 2, the shallow layer. Ruby. Let's start with Ruby. Ruby became popular because it focused on something unusual for its time: developer happiness. It was designed to feel natural to write, readable, expressive, almost conversational. That made it especially popular for web development, largely thanks to the Ruby on Rails framework. For a while, Ruby on Rails powered a massive wave of startups. Companies wanted to build fast, iterate quickly, and ship products without fighting the language. Interesting fact: the creator of Ruby, Yukihiro Matsumoto, has openly said that Ruby was designed to make programmers happy, not machines. Ruby was created in 1995, but its peak popularity came years later. Today, it's quieter, still used, still respected, but no longer dominating headlines. Ruby didn't disappear. It just settled down. Swift. Next is Swift. Swift is Apple's modern programming language, created to replace Objective-C, which was notoriously hard to read and error-prone. Swift is popular because it's safer, faster, and far more approachable than what came before it. If you're building apps for iPhones, iPads, or Macs, Swift is usually the default choice. Swift was created in 2014, which makes it one of the newer languages in this iceberg so far. Interesting fact: Swift was introduced without warning at Apple's developer conference. Apple simply revealed it, and within minutes, developers were dissecting it live. Swift represents a shift, not just in syntax, but in how companies control ecosystems through programming languages.
Subscribe to the channel first. Yes, hurry up!
Kotlin lives right next to Java. It was created to fix Java's pain points without abandoning the Java ecosystem. Cleaner syntax, fewer crashes, better handling of errors. Kotlin became popular when Google announced it as the preferred language for Android development. Almost overnight, Android developers were pushed toward it. Kotlin was first released in 2011, but its real explosion came years later after Google's endorsement. Interesting fact: Kotlin is fully interoperable with Java, meaning you can mix both languages in the same project. That's one reason adoption was so fast. Kotlin doesn't try to replace Java everywhere. It just quietly improves it. TypeScript. Now we get to TypeScript. TypeScript exists because JavaScript is powerful, but chaotic. JavaScript allows almost anything, which is great for flexibility but terrible for large code bases. TypeScript adds structure, rules, and type safety on top of JavaScript. TypeScript is popular because it makes large projects manageable. Teams can catch bugs before code ever runs. TypeScript was created in 2012 by Microsoft. Interesting fact: TypeScript code doesn't actually run. It gets compiled into JavaScript. The browser never sees TypeScript at all. TypeScript represents a trend you'll see again and again as we go deeper. Language is created not to replace something, but to control it. Go, also known as Golang, was created at Google. It was designed to be simple, fast, and scalable. Go shines in backend systems, networking tools, and cloud infrastructure. Go became popular because it handles concurrency extremely well without complex syntax. It's easy to deploy, easy to read, and difficult to overcomplicate. Go was released in 2009. Interesting fact: Go intentionally leaves out many features found in other languages. No generics for years, limited abstraction. This was a deliberate choice. Go is opinionated. It tells developers how to write code instead of asking. Rust is where this tier starts to feel intense. Rust is popular because it promises memory safety without sacrificing performance. That's a big deal in systems programming, where bugs can cause massive security issues. Rust prevents entire classes of errors at compile time, but the trade-off is complexity. Rust demands that you understand what the computer is doing. Rust was first released in 2010, and its growth has been slow but extremely loyal. Interesting fact: Rust has repeatedly ranked as one of the most loved programming languages in developer surveys, even among people who admit it's hard to use. Rust doesn't try to be easy. It tries to be correct. R. Finally, we have R. R is a language built specifically for statistics, data analysis, and visualization. It's deeply tied to academia, research, and data science. R is popular in fields like biology, economics, and social sciences, where statistical analysis matters more than software engineering practices. R was created in 1993. Interesting fact: R is named after the first letter of its creators' names, not after anything technical. R feels very different from most programming languages. It's not trying to be general. It's trying to be precise. And that's Tier 2. These languages aren't obscure, but they aren't neutral either. Each one represents a belief about how programming should work, how strict it should be, how safe it should be, how much freedom developers should have. From here on, things get less friendly. In the next tiers, we move away from popularity and toward history, academia, and experiments that shaped modern computing, whether they succeeded or not. This is hidden instruction. Let's keep going deeper. Getting deeper. At this point, the iceberg starts to change. These languages aren't chosen because they're trendy or easy. They exist because someone had a very specific idea of what programming should be. Some of them were ahead of their time. Some of them are still quietly running critical systems. And some of them feel like they were designed for a completely different world. Perl. Let's start with Perl. Perl was once everywhere. In the late 1990s and early 2000s, Perl powered huge parts of the web. System administrators loved it. Early web developers relied on it. It was fast to write, extremely flexible, and capable of doing almost anything. That flexibility came at a cost. Perl has a reputation for being unreadable. There's even a famous phrase associated with it: there's more than one way to do it. That philosophy gave programmers freedom. but it also made Perl code incredibly hard to maintain. Perl was created in 1987. Interesting fact: Perl is often described as a language that rewards cleverness. The problem is that clever code becomes unreadable code very quickly. Perl didn't vanish overnight. It slowly faded as people started valuing clarity over cleverness. Scala sits in an interesting place. It runs on the Java virtual machine, just like Java, but it mixes object-oriented programming with functional programming. Scala was designed to be powerful and expressive. In theory, it lets developers write very concise, elegant code. In practice, Scala can become extremely complex. Scala was created in 2004, and it found a home in large data processing systems, especially at companies dealing with massive amounts of data. Interesting fact: Scala code can be so abstract that two Scala developers might completely disagree on how the same program should be written. Scala isn't beginner-friendly. It's designed for people who already have strong opinions about programming. Haskell is where things start to feel alien. Haskell is a purely functional programming language. That means it avoids changing state, avoids side effects, and treats computation as the evaluation of mathematical functions. This makes Haskell extremely powerful for reasoning about code. It also makes it extremely difficult for most programmers to learn. Haskell was first standardized in 1990. Interesting fact: in Haskell, many programs describe what the result should be, not how to compute it. Haskell isn't trying to be practical for everyone. It's trying to be correct in a very strict mathematical sense. Lua is much smaller but very intentional. Lua was designed to be embedded inside other programs. It's lightweight, fast, and easy to integrate. That's why Lua is everywhere in games. Game engines use Lua for scripting behavior, AI, and game logic while keeping performance-critical code in other languages. Lua was created in 1993. Interesting fact: Lua is widely used in games you've probably played, even if you never realized it. Lua doesn't try to do everything. It does one thing very well. Dart. Dart exists because of a very modern problem. Google created Dart as a language for building user interfaces, especially across platforms. It became most well-known through Flutter, which allows developers to build mobile apps for multiple platforms from one codebase. Dart was first released in 2011. Interesting fact: Dart was originally intended to replace JavaScript in the browser. That plan failed, but Dart survived by finding a different niche. Dart is a reminder that languages don't always succeed at what they were designed for. Sometimes they succeed somewhere else. Elixir. Elixir is built on top of something much older. It runs on the same virtual machine as Erlang, a language designed for telecom systems that must never go down. Elixir was created in 2011 and focuses on concurrency, fault tolerance, and scalability. Interesting fact: systems written in Elixir can lose parts of themselves and keep running without crashing. Elixir feels modern, but it's standing on decades-old ideas. This is a pattern that comes up again and again as we go deeper. Julia. Julia was created to solve a specific frustration. Scientists and researchers wanted a language that was easy to write like Python but fast like C. Julia was released in 2012, and it was designed specifically for numerical and scientific computing. Interesting fact: Julia uses just-in-time compilation to achieve high performance while keeping readable syntax. Julia is still niche, but deeply respected in scientific circles. At this depth, you can start to feel a shift. These languages aren't chasing popularity. They're chasing ideals. Now we go deeper. This is where age starts to matter. Fortran. Fortran is one of the oldest high-level programming languages still in use. It was created in 1957. Despite its age, Fortran is still used today in physics, engineering, climate modeling, and scientific simulations. Interesting fact: NASA and research institutions still rely on Fortran because decades of tested code are difficult to replace. Fortran proves something important. A language doesn't have to be modern to be relevant. It just has to work. COBOL. COBOL feels ancient. It was created in 1959, designed specifically for business and financial data processing. Banks, insurance companies, and governments still run massive COBOL systems. Interesting fact: when legacy COBOL systems fail, entire institutions can grind to a halt. COBOL is often mocked, but it quietly moves enormous amounts of money every day. Lisp. Lisp is older than most programmers. It was created in 1958, and many of its ideas are still considered advanced today. Lisp introduced concepts like garbage collection, recursion, and code that can modify itself. Interesting fact: in Lisp, code and data share the same structure, which allows for extremely powerful abstractions. Lisp influenced many modern languages, even if most developers never realize it. Erlang. Erlang was designed for a world where failure is unacceptable. Created in 1986, Erlang was built for telecom systems that must run continuously for years. Erlang treats failure as normal. Processes crash, restart, and recover automatically. Interesting fact: Erlang systems are designed so that crashing is not an error, it's expected behavior. This mindset feels strange at first, but it changes how you think about software. Ada. Ada was created for safety. Released in 1980, Ada was designed for military, aerospace, and safety-critical systems. Errors in these systems aren't inconvenient. They're dangerous. Interesting fact: Ada enforces strict rules at compile time to prevent entire classes of bugs. Ada is rarely trendy, but when correctness matters more than speed, it's still trusted. Prolog. Prolog doesn't work like most programming languages. Instead of telling the computer how to solve a problem, you describe the problem and let the system figure out the solution. Prolog was created in 1972 and is associated with logic programming and artificial intelligence research. Interesting fact: Prolog programs often look more like rules than instructions. Prolog feels less like programming and more like reasoning. APL. APL looks wrong. It uses mathematical symbols instead of words. The code is dense, symbolic, and nearly unreadable to outsiders. APL was created in 1966. Interesting fact: APL programs can be extremely short, doing massive computations in just a few characters. APL is powerful but hostile. It assumes the reader already understands its worldview. At this depth, programming stops feeling universal. Languages become cultures. Communities form around ideas, not convenience. And below this layer, programming stops caring whether humans understand it at all. At this depth, programming stops pretending to be practical. These languages were not created to solve real-world problems. Some were jokes, some were experiments, some were acts of rebellion, and some feel like they exist purely to test how far the idea of a programming language can be stretched before it breaks. Brainfuck is exactly what it sounds like. It was created in 1993 as an experiment in minimalism. The entire language consists of just 8 commands. That's it. No keywords, no variables, no readable structure. Despite this, Brainfuck is fully Turing complete, meaning it can theoretically compute anything any other programming language can. Interesting fact: a simple Hello World program in Brainfuck is dozens of characters long and almost impossible to understand without a guide. Brainfuck isn't meant to be used. It's meant to exist. WHITSPAC. Whitespace takes the idea even further. In whitespace, only spaces, tabs, and newlines are meaningful. Every visible character is ignored. That means a whitespace program looks like a blank file. It was created in 2003 as a joke and a challenge. Interesting fact: you can hide an entire whitespace program inside a normal-looking text file, and most editors won't even show it. Whitespace turns programming into something invisible. Code that hides in plain sight. INTRCAL. INTRCAL was created in 1972, and it was designed to be intentionally hostile. The goal wasn't to be useful. The goal was to be as different from existing languages as possible. INTRCAL forces programmers to write code that feels backwards. It introduces pointless rules, confusing syntax, and features that actively make programming harder. Interesting fact: INTRCAL requires programmers to be polite. Certain commands must include please, or the compiler may refuse to run. INTRCAL doesn't reward understanding. It punishes expectation. LOLCODE. LOLCODE looks like a meme because it is one. It was created in 2007, inspired by early internet low LCAT culture. Programs are written in exaggerated internet slang. Variables, conditions, and loops all exist, just disguised as jokes. Interesting fact: despite the syntax, LOLCODE is fully functional and can run real programs. LOLCODE exists at the intersection of humor and absurd dedication. Someone didn't just joke about this. They finished it. Arnold C. Arnold C. is built entirely out of Arnold Schwarzenegger quotes. It was created in 2011 as a parody language, but like many languages down here, it actually works. The main function is called It's Showtime. Conditionals and loops are built from movie references. Interesting fact: the language was originally created for a programming contest joke and then expanded into a full interpreter. Arnold C. turns pop culture into syntax. Chicken. Chicken is a language where the only valid word is chicken. Every program consists entirely of the word chicken, repeated over and over again. It was created as an esoteric joke language. Interesting fact: the meaning of a chicken program depends entirely on how many times the word chicken appears and where. Chicken strips programming down to pure pattern. At this point, readability is gone. BFUNG. Bfunge breaks a rule most programmers never think about. Code doesn't have to run in a straight line. Bfunge is a two-dimensional programming language. The instruction pointer can move up, down, left, or right across the code. It was created in 1993. Interesting fact: Bfunge programs can loop in physical space, creating logic that looks more like a maze than code. Bfunge turns programming into navigation. At this depth, things start to feel less like jokes and more like challenges. Now we move into languages that actively resist the idea of being understood. MALBOLG. Malbolge is infamous. It was created in 1998, and it was explicitly designed to be almost impossible to program. The language uses self-modifying code, confusing instructions, and rules that change how the program behaves as it runs. Interesting fact: for years after its creation, no one knew how to write a valid Malbolge program by hand. Early programs were generated by brute force. Malbolge isn't difficult by accident. It's difficult by design. HQ9+. HQ9+ is a joke language with almost no functionality. It has exactly 4 commands. 1 prints hello world. 1 prints the source code. 1 prints the lyrics to 99 bottles of beer. And 1 does nothing. It was created to mock the idea of language design. Interesting fact: HQ9+ includes a command that has no observable effect whatsoever. It exists to waste your time. Piet doesn't look like code. It looks like abstract art. Programs in Piet are images. The logic is determined by how colors change and how blocks of color connect. Piet was created in 2001. Interesting fact: a Piet program can be framed and hung on a wall and still technically be executable code. At this level, programming becomes visual. VLATO. Velato pushes things even further. Velato programs are written as music, specifically MIDI files. The pitch, timing, and structure of the music define the program logic. Velato was created in 2009. Interesting fact: you can listen to a Velato program and have no idea whether it does anything at all. Programming becomes auditory. SHAKSBRE. In Shakespeare, programs are written as plays. Characters are variables. Dialogue is logic. Acts and scenes control flow. It was created in 2001. Interesting fact: a Shakespeare program can look like legitimate dramatic literature while performing calculations behind the scenes. At this point, code becomes theater. ROCKSTAR. Rockstar was created in 2018. Programs are written to resemble song lyrics and rock ballads. Variables are poetic. Logic is metaphorical. Syntax is intentionally vague. Interesting fact: Rockstar was inspired by a joke about programming languages sounding like song lyrics, and someone decided to make it real. Rockstar turns ambiguity into a feature. Down here, the idea of best practices no longer exists. These languages don't want to help you. They don't want to scale. They don't even want to be clear. They exist to test boundaries. And beneath this layer, programming stops feeling playful. It starts feeling personal. Final tier, the abyss. At this depth, programming stops being theoretical. It stops being about efficiency, syntax, or design patterns. Down here, programming languages exist because of people. Their beliefs, their isolation, their need to impose meaning on machines. This is the bottom of the iceberg. TempleOS and HOLYC. TempleOS is not just a technical project. It's a personal one. TempleOS is an operating system created almost entirely by a single individual, Terry Davis. Terry was a highly skilled programmer who also suffered from schizophrenia. Over time, he became convinced that God was directly communicating with him. According to Terry, he was instructed to build a perfect operating system. Something pure, something uncorrupted, a digital third temple. That system became TempleOS. TempleOS includes its own programming language called HolyC, a modified version of C designed specifically for this environment. The system runs in a fixed resolution, uses a limited color palette, has no networking support by design. Terry believed networking would introduce corruption and external influence. Despite everything surrounding its creation, TempleOS is technically impressive. It boots quickly, it is stable, and it was built almost entirely alone. This is what makes the story difficult. Temple OS is not a joke. It's not meaningless. It's the result of a brilliant mind operating under severe psychological strain. Terry Davis died in 2018. Temple OS remains archived and studied today, not because it's practical, but because it represents something deeply human. The God Protocol. Terry often spoke about a form of divine communication, sometimes referred to as a God protocol. According to him, Holy See and were not just tools. They were part of a system meant to communicate with God directly. There is no complete specification for this idea. Only fragments remain. Forum posts, code comments, video recordings. Whether viewed as belief, delusion, or tragedy, it represents a point where programming and faith become inseparable. At this depth, intent matters more than function. Lost Programming Languages. Not all languages disappear publicly. Some simply vanish. There are programming languages that once existed but no longer do. No compiler, no documentation, no runnable examples. Only brief mentions in academic papers. Broken links. Archived references. Some were created to support a single research project and were never intended to survive beyond it. When the hardware disappeared, the language disappeared with it. These languages are not deprecated. They are effectively extinct. Classified and internal languages. Then there are languages we may never see. Internal tools built by intelligence agencies, military systems, or private research groups. Languages designed for very specific purposes, never intended for public release. If they exist, they are undocumented by design. Large organizations routinely create domain-specific languages that never leave internal networks and are discarded when the project ends. Some languages are not hidden because they are dangerous. They are hidden because they are disposable. AGNERATED communication systems. As artificial intelligence has advanced, something unusual has begun to appear. In some experiments, AI systems develop internal communication structures. They resemble languages, but they are not designed for human understanding. When optimizing for efficiency, AI often abandons human-readable patterns entirely. These systems are structured, consistent, and difficult to interpret without translation layers. They are not programming languages in the traditional sense, but they are systems of meaning that humans did not design. Quantum Programming Languages. Quantum computing introduces another fracture. Quantum programming languages do not behave like classical ones. They operate on probability, uncertainty, and superposition. Programs describe possible outcomes rather than fixed instructions. The logic does not map cleanly to everyday intuition. At this level, programming is no longer about control. It becomes about observation. The dead languages. Finally, there are languages with no living users. No active developers. No communities. No one left who truly understands them. They still exist in archives, frozen in time. Like spoken languages with no remaining speakers, they can be studied but not lived. At the surface, programming feels clean and logical. But as you descend, it becomes clear that programming languages are not just tools. They are reflections of culture, of obsession, of belief, of the people who created them. Some were built to be efficient. Some were built to be expressive. Some were built for no one at all. And some exist only as fragments, memories, or warnings. This was the Programming Languages Iceberg. You've been watching Corrupted Files. If you made it this far, thank you for staying with the descent. And remember, The deeper you look into systems, the more you start to see the people behind them.